So next in our list of intermolecular forces is dipole-dipole interactions. Now you're actually kind of already familiar with this concept, so let's take it back to basically elementary or middle school physics. A dipole is something with two poles, and the thing that you know that has two poles is a magnet. So if you look at a magnet, we have a north pole and a south pole. And if we put two magnets close together, what they want to do is they want to align in such a way that the north poles are touching and the south poles are touching. The same thing is going to be true for molecules that undergo dipole-dipole interactions. We're going to have a positive in the molecule, a negative in the molecule, and they're going to align with each other so that they have positive-negative interactions. Now, the big thing with dipole-dipole interactions is, one, we're going to get them because we have big electronegative differences between two atoms. So we see this with carbonyl groups, carbon double bound to oxygen. Now, in a later video or another video, I'm going to talk about hydrogen bonding. The big thing here is we don't have hydrogen bonding. So when we have dipole-dipole interactions, the bonding we're seeing is purely due to electronegativity differences between the two atoms, not any types of exchanges of hydrogens or any type of like ionic compounds being formed. So an example of dipole-dipole interaction. If we look at something like formaldehyde, COH2. If we look at the electronegativity of the different atoms, we see that carbon is more electronegative than hydrogen, and oxygen is more electronegative than carbon. So overall, we end up with a negative charge on the oxygen and positive charges on our hydrogens. Now, let's say we have two formaldehyde molecules come close together. They're not going to want to stack on top of each other like this. What they'd much rather do is stack like this. Where we have the positive oxygen on one side and the positive hydrogens on the right side and the negative oxygen on the left side. And what will happen is that these carbons and oxygens will be attracted to each other because they have opposite charges. Now, they're not truly charged, but they have electronegativity. Oxygen has a lot of electrons around it because it's more electronegative than carbon, and the hydrogen doesn't have a lot of electrons around it because it's less electronegative than carbon. We'll also see on the other side of the molecule the oxygen interacting with the other hydrogens. Now, your dipole-dipole interactions are kind of, in terms of the scale, the mid-range interactions. So these are pretty strong interactions. They are much stronger than van der Waals, but they're not as high as the hydrogen bonding. But for organic molecules that contain these strong these strongly polarized bonds, like carbon between oxygen or carbon between fluorine, this is the type of interaction we see. Now, the complications with dipole-dipole interactions. I'm showing you very simple molecules. Let's say I build something a little bit more complicated. Now, in order to get dipole-dipole bondings, we have to have big electronegativity differences between two atoms, and we have that between carbon and oxygen. But let's say we have something like carbon-hydrogen. Carbon and hydrogen have different electronegativities, yes, but the electronegativity differences aren't that big. So we can't sit back and say that carbon and hydrogen are truly polar bonds. And so we have this chunk of the molecule that's polar, giving rise to our dipole-dipole interactions. But we have the rest of this, which is nonpolar. So only part of this molecule is going to participate in dipole-dipole interactions. The rest of it, these nonpolar carbon CH chains, aren't going to participate at all. So when we talk about dipole-dipole interaction, another thing to recognize with these molecules is that only part of the molecule may undergo dipole-dipole interaction. The rest may be nonpolar and have to undergo dispersion forces, or it may be the weight that affects it. So I guess what I'm just trying to tell you with this is that for simple molecules, dipole-dipole is clearly set. You have a positive in the molecule, you have a negative in the molecule, those two are going to match up. When you start getting to higher level chemistry courses and you start dealing with these big organic molecules, keep in mind though, dipole-dipole might not be the only interactions going on.